Every day, cellular aerobic metabolism produces roughly 15,000 millimoles of carbon dioxide. Because carbon dioxide is a volatile acid, this massive metabolic load is cleared effortlessly through continuous alveolar gas exchange in the lungs. However, metabolism also generates a secondary byproduct, roughly 70 millimoles of fixed, non-volatile acids, including lactic, phosphoric, and keto acids. The lungs are completely incapable of excreting these fixed acids. Because they cannot be exhaled, they accumulate directly in the blood. This is the Henderson-Hasselbalch equation. It defines arterial pH by calculating the ratio between the bicarbonate concentration in the numerator and the partial pressure of carbon dioxide in the denominator. If fixed acids drive the arterial pH below 7.35, the patient enters a lethal state of acidemia. To maintain this mathematical ratio against a continuous influx of fixed acids, the body triggers a sequential, three-tiered defense: chemical buffering, respiratory compensation, and definitive renal correction. Surviving severe metabolic acidosis requires bridging the time gap between instantaneous chemical defenses and the days-long process of complete renal clearance. The response begins in seconds. As fixed acids enter the extracellular fluid, they immediately encounter the first line of defense. This diagram illustrates the open bicarbonate carbonic acid buffer system. Free hydrogen ions bind to circulating bicarbonate to form carbonic acid. This intermediate molecule rapidly dissociates into carbon dioxide and water, allowing the newly formed CO2 to be exhaled. Under a severe acid load, the extracellular buffers saturate rapidly. The remaining free hydrogen ions are forced to cross the cell membrane, seeking intracellular buffers like hemoglobin. This movement is governed by the rigid physical requirement of electroneutrality. For every positively charged hydrogen ion that enters the cell, a positively charged potassium ion must be ejected into the extracellular fluid to maintain charge balance. This transcellular ion shift drives the clinical presentation of hyperkalemia, a characteristic finding in patients presenting with acute metabolic acidosis. Immediate chemical buffering successfully prevents a fatal collapse in blood pH. It achieves this by severely depleting the body's bicarbonate reserves and triggering a dangerous systemic potassium imbalance. As minutes turn into hours, the systemic defense activates. Specialized chemoreceptors located in the medulla and the carotid bodies detect the dropping extracellular pH. They trigger an efferent mechanical response, a massive increase in respiratory rate and tidal volume. Clinically, this deep, labored breathing is recognized as Kussmaul respiration. Returning to the Henderson-Hasselbalch equation, we see the effect of this hyperventilation. By blowing off excess carbon dioxide, the lungs actively drive down the arterial partial pressure of CO2, inducing a state of hypocapnia. Shrinking the denominator mathematically compensates for the severely depleted bicarbonate numerator. The overall ratio stabilizes, arresting the fall in pH near the 7.35 boundary. Respiratory compensation is strictly a stopgap measure. It can never achieve complete physiological correction, and it does absolutely nothing to replace the loss of bicarbonate or excrete the original fixed acid. True correction takes days, shifting the physiological burden entirely to the glomerulus and the proximal convoluted tubule of the kidney. To resolve the acidosis, the kidney must satisfy a dual requirement. It must perfectly preserve the existing buffer supply and then generate brand new buffers. The glomerulus filters approximately 4,320 millimoles of bicarbonate every day. If this is lost in the urine, the acidosis will rapidly worsen. All of it must be aggressively reabsorbed. This cross-section of a proximal tubule cell shows the apical transport mechanism. The cell secretes a hydrogen ion into the tubular lumen by exchanging it for a filtered sodium ion. In the lumen, the secreted hydrogen binds to the filtered bicarbonate, forming carbonic acid. Luminal carbonic anhydrase instantly breaks this down into carbon dioxide and water, which freely diffuse across the membrane into the cell. Inside the cell, intracellular carbonic anhydrase reverses the reaction, converting the carbon dioxide and water back into a hydrogen ion and a free bicarbonate ion. This reformed bicarbonate ion then exits via the basolateral membrane, safely returning to the peritubular capillaries. Notice what happened to the secreted hydrogen ion. It was consumed in the lumen to form water. Because of this massive transport process results in zero net acid excretion. Proximal tubule reabsorption merely conserves the baseline. To actually clear the 70 millimoles of fixed metabolic waste, the kidney must utilize a completely different cellular mechanism further down the nephron. Moving deeper into the late distal tubule and collecting ducts, we reach the primary site of acid excretion, the alpha intercalated cells. These cells execute the first generative mechanism, the excretion of titratable acid, using filtered inorganic phosphate. This diagram shows an alpha intercalated cell utilizing ATP-driven hydrogen pumps. These pumps force hydrogen into the lumen against a massive concentration gradient, achieving a urine pH as low as 4.5. The secreted hydrogen is permanently trapped by filtered phosphate to form a titratable acid. For every single hydrogen ion locked away in this manner, one entirely new molecule of bicarbonate is generated inside the cell and added to the blood. During severe metabolic acidosis, the finite supply of urinary phosphate buffers is quickly exhausted. The kidney responds by activating a scalable, high-capacity defense mechanism, ammoniogenesis. A drop in intracellular pH triggers the proximal tubule to upregulate the deamination of the amino acid glutamine. This produces ammonia, a lipid-soluble molecule that diffuses freely into the collecting duct lumen. Here, the ammonia acts as a chemical sink. It binds to a secreted hydrogen ion to form ammonium. This initiates a process called ion trapping. Because ammonium is positively charged, it cannot cross the lipid membrane back into the cell. The acid is permanently trapped in the urine for excretion. Strictly through the excretion of titratable acids and ammonium, the kidney permanently clears the fixed acid load and mints the new bicarbonate required to survive. Zooming out to a systemic view, we observe the physiological state after several days of successful compensation. In the Henderson-Hasselbalch equation, the lungs continue to hold the carbon dioxide denominator low, while the kidneys steadily drive the bicarbonate concentration back to normal levels, resolving the pH. An arterial blood gas reading maps where a patient is located along this temporal defense cascade. As renal correction succeeds, the initial emergency mechanisms unwind. The transcellular shift reverses, hydrogen exits the cells and potassium rushes back in, requiring careful clinical monitoring to prevent rebound hypokalemia. Acid-base homeostasis is a dynamic, multi-organ transfer of the acid burden, passing from the finite capacity of extracellular buffers to the mechanical mitigation of the lungs, and finally to definitive eradication by the kidneys.